Welcome to the Deep Dive, your shortcut to being well-informed. Today, we're plunging into one of the most remarkable stories in modern mathematics, the groundbreaking achievement of Yitang Zhang and his work on prime numbers.
It's a fantastic topic, really exciting stuff.
We've got a fascinating stack of sources for this deep dive, from excerpts of the paper itself to detailed study guides, historical timelines, and insightful briefings. Our mission isn't just to tell you what Zhang proved, but to take you on a journey through how he built his argument step by step, really following the structure of his brilliant proof. It's like a mathematical detective story.
It absolutely is. Zhang's paper, Bounded Gaps Between Primes, is a landmark. For the first time, it showed something truly astonishing, that even though prime numbers appear to pop up, well, somewhat randomly along the number line, they don't always get infinitely far apart.
Okay.
There's a finite limit to how wide the gaps between consecutive primes can be. It's a profound testament to mathematical ingenuity, really.
Okay, let's unpack this then. For centuries, mathematicians have been utterly fascinated by prime numbers. You know, those numbers only divisible by 1 and themselves. One of the most famous unsolved problems connected to them is the twin prime conjecture. What is it, and how does Zhang's work, this whole idea of bounded gaps, fit into that bigger picture?
Right. The twin prime conjecture, at its heart, asks if prime pairs that are just two numbers apart, like say 3 and 5, or 5 and 7, keep popping up infinitely often, no matter how far out on the number line you go.
Forever.
Forever, yeah. Mathematically, it asks if the smallest possible gap between infinitely many consecutive primes is exactly 2. Now, Zhang's paper didn't prove they were exactly 2 apart.
Right, that would have been the full conjecture.
Exactly, but he proved that these gaps don't just explode infinitely. There's a definite finite ceiling to how wide they can get. He gave an actual number, although the number itself wasn't the main point. It was showing it was finite.
So, not necessarily 2, but definitely not infinity.
Precisely. It's an enormous step toward the twin prime conjecture.
So he proved the gaps don't grow infinitely large. That's a huge conceptual leap, moving from maybe to definitely finite. But Zhang wasn't the first to chip away at this problem, right? Others had gotten incredibly close before him.
That's right. Before Zhang, there was the groundbreaking work of Goldston, Pintz, and Yıldırım, often just called GPY.
GPY.
In their 2009 paper, they proved that if primes satisfied a certain condition called a level of distribution, basically, how evenly they're spread across arithmetic progressions, then bounded gaps would exist.
Okay.
And the Bombieri-Vinogradov theorem already gave them a significant part of the way there, a level of distribution of 12. GPY needed just a tiny bit more, like 12 plus epsilon.
So they were almost there.
They were so close. The GPY team themselves famously described the remaining hurdle as being within a hair's breadth.
Wow. Here's where it gets really interesting then. Imagine reaching for a distant peak, only to find this invisible, razor-thin crevasse right before the summit. That's kind of where GPY left us. Zhang's brilliance was in figuring out exactly how to build a bridge across that, well, that seemingly impossible gap. What was his overall strategy, drawing from the notation and sketch of the proof section in his paper? How did he even begin to tackle proving these bounded gaps?
Well, Zhang's method is a refinement of that GPY sieve, building directly on their insights, but adding some crucial new ingredients. His core strategy was to evaluate and compare two specific, very large sums, which he calls $6 and 3 and 2.
Okay, $6 and $6.
Now think of it like this. He needed to show that a certain mathematical expression involving these sums was positive. If he could prove that inequality, $2 log 3x and 1 of dollars, it would force the existence of those bounded prime gaps.
So it's all about comparing these two quantities. What do Sadayu and 1 represent, roughly?
Datrel essentially measures the average behavior of numbers within a certain range, weighted by a function lambda. Delical is similar, but it specifically looks for sums involving theta plus high, where theta basically lights up if the number is prime. So theta 2 is trying to detect primes within a specific structure.
Okay, so Sada 1 is the baseline, and Sada 2 is looking for the prime signal.
Kind of, yeah. He was essentially asking, is the prime signal strong enough, compared to the baseline, to guarantee at least 2 primes close together?
And the ultimate goal was showing that Sada 2 is significantly larger than Sada 1 by that logarithmic factor, specifically $2, log 3/5. What does that inequality, once you prove it, actually tell us about primes?
If this inequality holds for numbers large enough, which Zhang showed it does, it mathematically implies that within a specific basket of numbers, a set called an admissible k-dollar tuple, like nalm plus h1 and nalm plus h2, there must be at least 2 primes.
Ah.
This directly proves the existence of a finite gap between primes, bounded by the largest difference among the dollar's days. The size of this basket, K to dollars, is crucial. Zhang chose a remarkably large one. K to dollars equal 3.5 times 166.
3.5 million. And this admissible set, as defined in the paper, is basically a collection of possible gap sizes, the K to dollars, that could plausibly contain primes, right? It's structured so it avoids obvious conflicts with small prime divisors.
Exactly. It ensures you're not looking in a place where primes are impossible for trivial reasons. And the lambda n function acts as a weighting tool designed to pick out numbers where this tuple 1n plus h1 and plus hk is more likely to contain primes.
And theta is essentially the prime indicator. This sets the stage for comparing $6 and $6.2s.
Right. Now, one of Zhang's key innovations, what he called his first observation in section 2 of the paper, tackled a major challenge that had stumped the GPY method. GPY couldn't quite get their critical inequality to hold unconditionally because of, well, stubborn error terms in their calculations.
That was the hair's breadth again.
That was the hair's breadth. The issue arose when trying to estimate certain sums related to sudden moles and SOD2 Let's call them T12 and T122.
So what did Zhang realize about these incredibly complex arithmetic sums? What was his aha moment here?
He had a truly brilliant insight. He looked closely at the structure of these sums, which involved summing over moduli, divisors, dollars. He realized that the contributions from terms where the modulus dollar had a large prime factor were actually, well, relatively small. Almost negligible in the grand scheme of things.
Interesting. So the really complicated bits involving large primes weren't actually driving the main value.
Pretty much. Imagine a giant tangled knot of equations the GPY method was getting stuck because some parts involving these large prime factors were just too messy to control precisely enough. Zhang's first observation was like finding a loose thread, realizing these terms weren't as critical as perhaps assumed.
That's a huge strategic insight. It sounds like simplification without losing the essence. So what did this observation allow him to do in terms of the formulas he was working with?
Exactly. It allowed him to impose a new simplifying constraint. He could essentially say, okay, let's only consider moduli dollars that are smooth or friable, meaning only has small prime factors. Specifically, dollar had to divide a product of all primes less than some d dollars was x delta, where delta was small, like 11,168.
Wow, that's quite a specific constraint.
It is, but it was strategically brilliant. It dramatically simplified the calculations for the main terms in $6.72 because he didn't have to worry about those troublesome large prime factors in Elters. Crucially, he showed this constraint didn't significantly reduce the size of the main terms he needed. It was a surgical strike.
Okay, that gets rid of one major headache. But that brings us to Zhang's second observation, which the paper itself calls the most novel part of the proof. With this new constraint on dollars, how did he then tackle the notoriously difficult error term, the part that measures the deviation from the expected distribution of primes? That's always the killer in these problems.
Right. The error term, often denoted L yellow, is always the beast. With the new constraint d' and a specific choice for another parameter dollar, related to how far you sum, del dls by 14 plus delta, Zhang found a revolutionary way to bound this error term, which looks roughly like sum dd2 dp sum delta.
That delta term represents the error in primes in arithmetic progressions, right?
Yes, it measures the difference between the actual number of primes and what you'd expect in a given progression modulo d2. Bounding this sum is critical. Zhang's crucial insight here, his second observation, is that if dollars is made of small primes, since d' until it is not too small itself, say d by 12 epsilon, then dollars can often be factored into two smaller parts, say
factorization again, like breaking it down.
Exactly. And importantly, this factorization teller can be done flexibly, where dollars is in a convenient range.
So this ability to factor dollars into tollers is really the key to controlling the errors. It's like being able to break a single unmanageable block into two smaller, more predictable pieces. Is that related to this idea of a well-factorable function?
Precisely. This clever factorization allows the characteristic function of the relevant moduli, the function that picks out the dollars he's summing over, to be treated as what's called a well-factorable function. This is a really powerful technique in analytic number theory, especially when dealing with sums over arithmetic progressions like the Bombieri-Vinogradov theorem.
Okay.
It essentially allows you to decompose the problem. Instead of tackling the error term for the full modulus dollars all at once, you can break it down based on the factors 3 and 2. This makes estimating the error term much more tractable. This whole line of argument culminates in his central technical result, Theorem 2.
Theorem 2, the big one.
Yes. Theorem 2 essentially states that this formidable error sum, SUI C, under his conditions, is acceptably small. Specifically, it's bounded by 6 Lauer, where a bell in their dollars is some large constant. This shows the error is small enough not to overwhelm the main term.
So Theorem 2 is the linchpin. Getting that result is the main battle. How does the paper then guide us through how he actually proved Theorem 2? It seems like sections 6 through 14 are dedicated just to that. That's a lot of paper.
It is. It's the technical heart of the paper. The strategy, which he lays out in section 6, combinatorial arguments, is to reduce the problem of estimating these error terms, the delta terms, to analyzing sums involving different types of functions, specifically Dirichlet convolutions.
Convolutions, like mixing functions together mathematically.
Sort of, yeah. An arithmetic function gamma can often be written as a combination of simpler functions, say gamma alpha beta, or something more complex. Zhang breaks down the analysis based on the structure of these convolutions.
And these are the famous type I, type 2, and type 3 estimates?
Exactly. Sections 7 through 12 handle type I and type 2 estimates. These generally deal with convolutions like gamma alpha beta, where one function is smooth and the other is arbitrary, or both are restricted in length.
How does he tackle those? What tools come into play?
Here, he employs a sophisticated technique known as the dispersion method, which has roots in work by Fouvry, Uwaniak, Bombieri, and Friedlander.
Okay, the BFI papers.
Right. The dispersion method is a way to estimate sums by, well, looking at how they disperse or vary. He combines this method very carefully with that crucial Dirichlet factorization idea from his second observation.
And what about the actual calculations? I heard mentions of some deep results even here.
Yes, to get the necessary precision, especially when the modulus dollars is close to $6 post, these estimates rely heavily on variants of Weil's bound for Kloosterman sums.
Kloosterman sums, those sound intimidating.
They are intricate exponential sums. Weil's bound, stemming from algebraic geometry, gives incredibly sharp estimates for them. Think of it like using a high-powered microscope to get the needed accuracy in the calculations. These bounds allow him to save just enough a small power of $6 compared to trivial estimates, which is critical.
Okay, so that's type I and type 2, using dispersion and Weil's bounds. What about type 3? Sections 13 and 14 deal with that. Sounds even harder.
It is. Type 3 estimates deal with more complex convolutions, perhaps like gamma alpha beta nu, where several functions are involved. These are often the trickiest.
So how does Zhang wrap this up? How does he conquer these type 3 estimates? What deep, maybe unexpected results are brought in here?
This is where Zhang pulls out, arguably, the deepest tool in the whole proof. He relies on a result known as the Birch-Bombieri theorem.
Birch-Bombieri.
And this theorem itself is founded on something absolutely fundamental. Pierre Delaine's proof of the Riemann hypothesis for varieties over finite fields, part of the Weil conjectures.
Wow. So we're going from prime gaps all the way to Delaine's proof of the Weil conjectures. That's incredible depth.
It really is. It shows the profound connections within mathematics. Zhang masterfully combines this deep result from algebraic geometry with his Dirichlet factorization trick. This combination allows him to save an additional crucial factor needed to bound these most challenging type 3 error terms. It's truly a tour de force, connecting seemingly disparate areas of number theory and geometry.
Okay, so after all these incredibly intricate estimations for type 1, 2, and 3, culminating in the proof of Theorem 2, how does this all feed back into the main argument? How does proving Theorem 2 let him finish the job with 17 additivers?
Right, so once Theorem 2 is established, confirming the error terms are under control, the rest of the proof, detailed mainly in sections 4 and 5, falls into place relatively smoothly.
Relatively.
Well, relatively speaking. In section 4, upper bound for S1, he calculates the upper bound for the baseline sum $70. Then, in section 5, lower bound for S2, using Theorem 2 to handle the error term, he derives the necessary lower bound for 2 the sum that detects primes. And
this is where he shows AH2 is bigger than $70 by that log factor.
Exactly. The final step, detailed at the end of section 5, is putting the bounds for $70 and $60 together, including the controlled error terms, and showing that the crucial quantity, $70 log 3 by mon twin, is indeed positive for large enough $6.
And that positive outcome forces the conclusion that K-dollar tuple that basket of $3.55 million numbers must contain at least 2 primes, which means there's a gap between primes no larger than the width of that basket. He proved bounded gaps exist.
Precisely. It's an incredible logical chain of arguments, built layer by layer, starting with the GPY framework, adding the 2 crucial observations about moduli, proving the monster theorem 2 by dissecting it into types and applying deep tools, and finally assembling the pieces to get that positive inequality.
What's truly fascinating here, as you mentioned, is the scale. $2 equals 3.5 times 160 secs, leading to a bound under $7 times 175. The paper even calls these numbers not optimal and crude. Why wasn't getting the best number the main goal?
Because the breakthrough was the existence proof. For decades, the question was open. Could the gaps between primes grow arbitrarily large? Zhang proved definitively no, they cannot. There is a finite bound. Establishing that conceptual fact was monumental. The specific number, 70 million, was just what his method yielded at that point. It was like proving you can cross the ocean, even if your first raft isn't the fastest or most elegant.
That makes sense. And this result absolutely changed the game for number theorists, didn't it? What doors did it open for subsequent research?
Oh, completely. It fundamentally altered perspectives on the twin prime conjecture and related problems. Before Zhang, while many believed in bounded gaps, the possibility of unbounded growth was still mathematically conceivable for some. His proof slammed that door shut.
Right.
And it immediately spurred this intense activity. People like James Maynard and independently Terry Tao, leading the Polymath project, saw Zhang's framework and realized they could refine parts of it, particularly the sieve weights related to lambda.
And they brought the bound down significantly, right?
Dramatically. Within months, Maynard and the Polymath project pushed the bound down from 70 million to, eventually, 246. A huge improvement, showing the power and flexibility of the underlying method Zhang had pioneered.
So what does this all mean for the future of the twin prime conjecture itself? Are we actually closer to proving that elusive gap of 2?
We're certainly closer conceptually. Zhang's work and the subsequent refinements proved the immense power of these refined sieve methods, combined with deep results from analytic and algebraic number theory. The path forward involves pushing these methods even further, finding new ways to optimize the sieve or handle the error terms even more effectively. The challenge is still immense. Getting all the way down to 2 requires fundamentally new ideas, perhaps. But the conceptual barrier has been broken. The game is afoot.
And that's our deep dive into Yitang Zhang's bounded gaps between primes. What started as a hair's breadth problem was bridged by brilliant insights, particularly those 2 key observations about handling moduli and factoring divisors, leading to a methodical proof built layer upon layer, just like following the steps in a paper. It's a prime example, pardon the pun, of turning a seemingly impossible wall into a fascinating, solvable puzzle.
It truly shows that even in the most abstract corners of mathematics, ingenuity matters. Combining existing tools, like the GPY sieve and Weil bounds, with novel observations about structure, like Zhang's factorization trick, can lead to profound breakthroughs. It's a testament to how persistence and really creative thinking can unlock problems that have stood for centuries. That first observation can change everything.
So what stands out to you? Thinking about this deep dive, maybe consider how many other long-standing problems in math or elsewhere might just be waiting for someone to look at a familiar piece in a slightly new way, make that first observation about seemingly minor terms, and unlock a whole cascade of new understandings, just like Zhang did. Join us next time on The Deep Dive.